In the vast emptiness beyond Neptune's orbit, where sunlight arrives as little more than a whisper of warmth, something stirs. The object moves through space with the patience of geological time, a dark nucleus no larger than a mountain, tumbling slowly end over end in the cosmic dark for 4.5 billion years. This visitor has wandered the outer reaches of the solar system, a remnant of the primordial disk that gave birth to worlds. Now, for the first time in its long journey, it feels the touch of our star's influence. The Comet 3 I/Atlas drifts inward along its elliptical path, carrying within its frozen heart the chemical memory of the early solar system. Its surface, darker than charcoal, absorbs what little sunlight reaches it at this distance. The temperature hovers near absolute zero, where molecular motion nearly ceases and time itself seems to slow. Yet even here, in this realm of perpetual winter, change begins its quiet work. Deep within the nucleus, ancient ices rest in crystalline structures that formed when the solar system was young. Water molecules lock together in hexagonal patterns, trapping bubbles of carbon monoxide, nitrogen, and methane. These gases have waited patiently in their frozen prison, preserved like messages from a time when planets were still coalescing from dust and debris. The comet remembers what the inner solar system has forgotten: the original composition of the stellar nebula, the chemical fingerprint of our cosmic birth, as 3 I/Atlas continues its inward journey, crossing the invisible boundary where Jupiter's gravitational influence gives way to the Sun's warming embrace. The first subtle changes begin. Solar radiation penetrates the outermost layers of the nucleus, causing individual molecules to vibrate with newfound energy. The process unfolds with extraordinary gentleness, like the first breath of spring touching a frozen lake. Only the most sensitive instruments can detect what is happening. A gradual increase in the comet's brightness as its surface begins the ancient dance of sublimation. The transformation occurs at the boundary between solid and gas, where ice skips the liquid phase entirely and becomes vapor. This is sublimation in its purest form, a molecular exodus that has repeated countless times throughout the history of the solar system. Each escaping molecule carries with it a fragment of the comet's chemical heritage, releasing gases that have not tasted sunlight for eons. The process creates no sound, no visible drama, only a gradual brightening that registers on photographic plates as a subtle shift in luminosity. Astronomers on Earth first noticed the change as a minor adjustment in the comet's apparent magnitude. Through their telescopes, 3 I/Atlas appears as little more than a fuzzy star, distinguished from the background only by its slow motion against the stellar backdrop. But careful measurements reveal something intriguing. The comet's color index begins to shift, where once it reflected light with a neutral, grayish hue characteristic of inactive nuclei. Now it shows the faintest hint of blue-green, the signature of emerging gases interacting with solar radiation. The mystery deepens with each passing observation. Comets typically brighten gradually as they approach the Sun, following predictable patterns established by decades of study. But 3 I/Atlas displays an unusual behavior. Its color changes appear to happen overnight, as if some internal switch has been activated. The spectral shift suggests the presence of diatomic carbon molecules, C2, which glow with their characteristic green emission when excited by ultraviolet light. Yet the comet remains too distant for such rapid activation. According to conventional models, ground-based observatories around the world begin coordinating their efforts, tracking the visitor's progress with increasing interest. Each night brings new data, revealing subtle variations in brightness and color that hint at complex processes occurring within the nucleus. The measurements accumulate like sedimentary layers, building a record of the comet's awakening that will puzzle researchers for months to come. What they are witnessing represents one of the fundamental mysteries of cometary science, the exact mechanisms by which these ancient time capsules transition from dormant wanderers to active, gas-producing bodies. The comet's nucleus continues its slow rotation, completing one turn approximately every 6 hours. This rotation creates a subtle rhythm in its brightening, as different regions of the surface face the sun in turn. Some areas appear more active than others, suggesting variations in composition or structure that formed billions of years ago. The irregular shape of the nucleus, revealed through careful analysis of the brightness variations, tells the story of countless impacts and gravitational encounters that have sculpted its form over cosmic time. As 3I/Atlas moves through the transition zone between the outer and inner solar system, it carries with it the accumulated gravitational memories of its long journey. Every close encounter with Jupiter, every perturbation by Saturn's massive presence has left its mark on the comet's orbital path. The ellipse it traces through space encodes a history of celestial mechanics that stretches back to the solar system's youth, when the giant planets migrated from their original positions and scattered countless comets into the distant Oort cloud. The sublimation process accelerates with almost imperceptible gradualness. More molecules escape the nucleus with each passing day, creating an expanding envelope of gas and dust around the solid core. This envelope, called a coma, remains invisible to all but the most sensitive detectors, yet it represents a fundamental transformation in the comet's nature. Where once 3I/Atlas was simply a dark rock tumbling through space, now it becomes something more dynamic, a small world actively losing mass to the solar wind, shedding pieces of itself in a slow dance with our star. The color shift that first caught astronomers' attention continues to evolve, revealing new spectral features with each observation. The initial blue-green tint gives way to more complex hues as different molecules join the sublimation process. Carbon monoxide begins to outgas, followed by traces of nitrogen and methanol. Each gas contributes its own signature to the comet's spectrum, creating a chemical fingerprint that researchers will study for years, searching for clues about conditions in the early solar system. In the growing coma, individual gas molecules move at speeds determined by temperature and molecular weight. The lightest gases, hydrogen and helium, escape most readily, while heavier molecules linger closer to the nucleus. This sorting process creates subtle gradients in composition that vary with distance from the core, like the layers of an invisible atmosphere too tenuous to trap heat or support weather, yet complex enough to bend and scatter light in measurable ways. The transformation of 3I/Atlas from a dark and inactive nucleus to an actively outgassing comet represents one of the most fundamental processes in the solar system, the awakening of ancient materials to the warming influence of our star. Each molecule that escapes carries information about the conditions that existed when comets first formed, preserving chemical records that planets have long since erased through geological activity. The comet becomes a library of the early solar system, written in the language of sublimating gases and encoded in the subtle shifts of reflected starlight. As this first section of the comet's story draws to a close, 3I/Atlas continues its patient journey inward, its color index still shifting in ways that challenge theoretical predictions. The overnight changes that first caught scientists' attention represent just the beginning of a months-long transformation that will reveal new puzzles about cometary behavior and the chemical heritage of our cosmic neighborhood. In the vast silence of space, the comet continues its ancient dance with the sun, marking time with the rhythm of sublimating ice and the gentle poetry of molecules returning to the void. The ancient ice within 3I/Atlas holds memories older than Earth's oceans. Crystalline structures formed in the primordial cold of the outer solar nebula begin their first awakening in 4 billion years, as solar photons penetrate the nucleus with increasing frequency. These are not ordinary ice cubes floating in a terrestrial freezer, but exotic frozen mixtures that preserve the chemical composition of interstellar space itself. water molecules interlocked with carbon monoxide, nitrogen, and methane in lattices that could only form in the absolute cold beyond the frost line. Each crystal remembers the temperature at which it formed, encoded in the precise angles between molecular bonds and the spacing of atomic arrangements. The ice carries within its structure the signature of stellar winds and cosmic radiation that bathed the early solar system, when the sun was younger and more variable in its energy output. Now, as warmth penetrates these ancient formations for the first time, the crystals begin to surrender their long-held secrets to the vacuum of space. The sublimation process unfolds with the patience of geological time compressed into astronomical moments. Individual molecules break free from their crystalline prisons not in violent explosions, but in gentle molecular escapes that occur one by one, like snow melting in reverse. The solid ice skips the liquid phase entirely in the vacuum of space, transforming directly into vapor that expands outward from the nucleus in invisible streams. Each escaping molecule carries with it the kinetic energy of its liberation, moving at speeds determined by the balance between solar heating and the gravitational pull of the comet's modest mass. Deep beneath the surface, where sunlight has never penetrated, pristine ice remains locked in formations that predate the formation of planets. These subsurface layers contain chemical ratios that reflect the original composition of the solar nebula, preserving isotopic signatures that tell the story of stellar nucleosynthesis in the star that died to create our solar system's raw materials. The ice holds within its molecular structure the debris of supernovae, the ash of red giants, and the condensed breath of stellar winds that blew across the galaxy billions of years before Earth existed. As the outermost layers sublime away, they expose slightly younger ice beneath, still ancient by human standards, but formed perhaps a few million years later in the comet's accretion history. This creates a subtle stratigraphy within the nucleus, layers of frozen time that record changes in the early solar system's chemical composition as planets formed and cleared their orbital paths. Each layer tells part of the story of how our cosmic neighborhood evolved from a chaotic disk of dust and gas into the orderly arrangement of worlds we observe today. The process of ice liberation creates its own microenvironment within the expanding coma. Water molecules, once freed from their crystalline constraints, begin to dissociate under the influence of solar ultraviolet radiation. The photodissociation process splits H2O into hydrogen and hydroxyl radicals, each carrying a characteristic spectral signature that astronomers can detect from Earth. This breakdown creates a cascade of chemical reactions that transforms the simple ice of the nucleus into a complex mixture of molecular fragments, each contributing to the comet's evolving color palette. Temperature gradients within the nucleus drive complex patterns of sublimation that vary with the comet's rotation. Areas facing the sun experience direct heating, while shadowed regions remain in the deep cold of space. This creates a day-night cycle on the comet's surface, where local noon might reach temperatures warm enough for vigorous outgassing, while midnight regions maintain their primordial freeze. The thermal cycles stress the nucleus, creating fractures and cracks that provide new pathways for gas escape, gradually altering the comet's internal structure. Trapped within the ice matrix are microscopic dust particles, the solid remnants of interstellar grains that served as condensation nuclei when the comet first formed. These particles, smaller than bacteria and darker than soot, become liberated as the surrounding ice sublimes away. Each grain carries its own story of cosmic wandering, having survived the destruction of its parent star and the journey through interstellar space before being incorporated into the growing nucleus of what would become 3Y/Atlas. The liberation of ancient ice creates an expanding sphere of influence around the comet, a region where escaped molecules interact with the solar wind and magnetic fields. This interaction zone, invisible to optical telescopes but detectable by radio astronomy, represents the comet's first tentative reach into the space around it. The boundary between the comet's influence and the general interplanetary medium shifts constantly as more gas escapes the nucleus, creating a dynamic interface that ebbs and flows with the rhythm of sublimation. Spectroscopic analysis reveals that not all the ice sublimes at the same rate. Water ice, the most abundant component, requires more energy to transition from solid to gas than the more volatile species like carbon monoxide and nitrogen. This creates a sequence of outgassing events as 3I/Atlas approaches the Sun, with the most volatile materials escaping first, followed by water, and finally, the more refractory compounds embedded deeper within the nucleus. Each phase of this process contributes different emission lines to the comet's spectrum, creating a temporal signature that reveals the nucleus's internal composition layer by layer. The awakening ice also carries with it dissolved gases that were incorporated during the comet's formation. Noble gases like argon and xenon, trapped within the crystal lattice for billions of years, escape along with the subliming water and carbon monoxide. These chemically inert elements provide some of the most valuable scientific information about conditions in the early solar system, since they cannot be altered by chemical reactions and preserve their original isotopic ratios unchanged since the comet's birth. As the ice continues its gentle transformation from solid to gas, it creates patterns of brightness variation that reflect the nucleus's irregular shape and non-uniform composition. Some regions of the surface contain more volatile materials than others, leading to localized jets of gas that emerge from specific areas as they rotate into sunlight. These jets, though barely detectable at the comet's current distance from the Sun, represent the first stirrings of the dramatic activity that will characterize 3I/Atlas's behavior as it continues its inward journey. The process of ancient ice awakening represents one of the most fundamental transitions in the solar system, the transformation of primordial materials from their frozen state of preservation into active participants in the ongoing dance between matter and energy that characterizes our cosmic environment. Each molecule that escapes the nucleus carries with it information about the conditions that existed when worlds were young and the solar system itself was learning the rhythms that would govern it for billions of years to come. The ice remembers what planets have forgotten, preserving in its crystalline structure the chemical signature of our cosmic birth and the slow processes that shaped the architecture of space itself. The first astronomers to notice the shift work through the quiet hours, when Earth's atmosphere steadies and starlight grows sharp, at observatories scattered across continents. Researchers peer through eyepieces and examine photographic plates with the methodical patience that defines their craft. What they discover defies the gentle predictability usually associated with distant comets. 3I/Atlas undergoes a color transformation that seems to unfold between one night's observation and the next, as if some invisible threshold has been crossed in the depths of space. The color index, a precise measurement that compares how an object appears in different wavelengths of light, serves as one of astronomy's most sensitive diagnostic tools. For months, 3I/Atlas has maintained the neutral gray signature typical of inactive comet nuclei, reflecting sunlight with the same spectral characteristics as charcoal or weathered stone. This consistency suggests a dormant world, its surface unchanged by solar heating and its interior locked in the deep freeze that has preserved it since the solar system's formation. Then, over the span of a single terrestrial night, something fundamental changes. The shift begins subtly in the blue portion of the spectrum, where wavelengths around 440 nanometers show a slight increase in intensity. This enhancement, barely detectable above the noise of atmospheric turbulence and instrumental uncertainty, represents the first whisper of molecular emissions from the comet's awakening nucleus. The additional blue light comes from excited carbon molecules, C2, which absorb ultraviolet solar radiation and re-emit it at longer wavelengths in a process called fluorescence. For C2 emission to become detectable, the comet must be producing substantial quantities of carbon-bearing gases. Yet 3I/Atlas remains too distant from the Sun for conventional models to predict such rapid activation. Simultaneously, observers detect a complementary enhancement in the green portion of the spectrum, centered around 510 nanometers. This signature belongs to the same carbon molecules in a different excited state, creating the characteristic blue-green hue that gives active comets their distinctive coloration. The appearance of both blue and green emission lines within hours of each other suggests that whatever process triggered the comet's activation affects multiple molecular species simultaneously, pointing toward a fundamental change in the nucleus's thermal environment rather than a gradual warming effect. The overnight transformation puzzles researchers familiar with the typically slow evolution of comet brightness and color as they approach the Sun. Most comets follow predictable curves of increasing activity, their brightening and spectral changes occurring over weeks or months as solar heating gradually penetrates their surfaces. The sudden appearance of molecular emissions in 3I/Atlas suggests either an unusually rapid response to solar heating or the involvement of processes not accounted for in standard cometary models. Some researchers propose that the comet's nucleus might contain unusually volatile materials that sublime at lower temperatures than typical cometary ices, while others suggest that internal heat sources might contribute to the unexpected activity. The color shift becomes more pronounced as observations continue through the following nights. Where 3I/Atlas once appeared as a neutral gray point of light indistinguishable from background stars except for its motion, it now displays the unmistakable spectral signature of an active comet. The blue-green coloration intensifies with each passing observation, indicating that the production of carbon-bearing gases continues to accelerate despite the comet's considerable distance from the Sun. This rapid evolution challenges theoretical understanding of cometary activation and suggests that 3Y/Atlas might represent a previously unobserved class of objects with unusual thermal or compositional properties. Photometric measurements reveal that the color change accompanies a corresponding increase in overall brightness. The comet's magnitude, a logarithmic scale that quantifies celestial object brightness, begins to decrease, indicating increasing luminosity at a rate that exceeds predictions based on its orbital position. This brightening occurs not through a uniform increase in reflected sunlight, but through the addition of new emission lines that contribute specific wavelengths to the comet's spectrum. The process transforms 3I/Atlas from a passive reflector of solar radiation into an active emitter of characteristic molecular signatures. Spectroscopic analysis reveals the complexity hidden within the apparent simplicity of the color shift. High-resolution instruments break down the comet's light into its component wavelengths, revealing a forest of emission lines that correspond to specific molecular transitions. Carbon molecules dominate the initial spectrum, but careful analysis also detects the signatures of CN radicals, fragments of hydrogen cyanide molecules broken apart by solar ultraviolet radiation. The presence of CN suggests that the nucleus contains more complex organic compounds than the simple ices typical of most comets, hinting at a formation history that might differ from the standard model of cometary accretion. The spatial distribution of the color change provides additional clues about the underlying physical processes. Rather than emanating uniformly from a point source, the blue-green emission shows subtle variations that suggest the presence of an extended coma, a tenuous atmosphere of gas and dust surrounding the nucleus. This coma, though far too faint to detect visually, becomes apparent through careful analysis of the comet's brightness profile. The fuzzy, extended nature of the emission indicates that gases escaping from the nucleus form an expanding envelope that scatters and re-emits solar radiation over a volume much larger than the nucleus itself. Advanced imaging techniques reveal structure within the developing coma that hints at non-uniform outgassing from the nucleus, rather than expanding symmetrically in all directions. The gas envelope shows subtle asymmetries that suggest localized sources of activity on the nucleus surface. These active regions, invisible at the comet's current distance, but detectable through their contribution to the overall emission pattern, indicate that the nucleus possesses a heterogeneous composition, with some areas more susceptible to solar heating than others. The irregular outgassing creates a complex three-dimensional structure within the coma that evolves as the nucleus rotates and different regions face the sun. Temperature measurements derived from the intensity ratios of different emission lines suggest that the gas within the coma maintains a temperature significantly higher than expected for the comet's distance from the sun. This thermal excess indicates that additional heating mechanisms beyond direct solar radiation might contribute to the nucleus's activation. Possible explanations include the release of crystallization energy as amorphous ice transitions to crystalline form, radioactive decay of incorporated isotopes, or exothermic chemical reactions between different molecular species as they escape the nucleus and interact within the expanding coma. The mystery deepens as researchers compare 3 I/Atlas with other comets observed at similar distances from the Sun. Database searches reveal no comparable cases of such rapid color index changes occurring overnight at distances where solar heating should be minimal. The comet's behavior appears unique in the historical record, suggesting either that it represents a rare class of object or that specific conditions during its current orbital approach have triggered unprecedented activity levels. This uniqueness makes 3 I/Atlas particularly valuable for understanding the diversity of cometary compositions and behaviors that exist within the solar system. Polarization measurements add another layer of complexity to the observations. Light scattered by dust particles within the coma becomes partially polarized, with the degree of polarization depending on the size, shape, and composition of the scattering particles. Analysis of polarized light from 3 I/Atlas reveals that the nucleus is producing dust along with gas, suggesting that the sublimation process liberates solid particles embedded within the ice matrix. The polarization signature indicates that these dust particles have sizes and refractive properties consistent with carbonaceous materials mixed with silicate minerals, providing insight into the solid component of the nucleus composition. Multi-wavelength observations across the electromagnetic spectrum reveal that the color change extends beyond visible light into infrared and ultraviolet portions of the spectrum. Infrared measurements detect thermal emission from warm dust particles heated by absorbed solar radiation, while ultraviolet observations reveal additional molecular emission lines not visible in optical wavelengths. The broad spectral coverage of the activity suggests that the processes driving the comet's transformation affect multiple physical and chemical systems simultaneously, creating a cascade of effects that manifest across the entire electromagnetic spectrum. As the third section of 3 I/Atlas's story concludes, the comet continues its transformation from a dormant wanderer into an active participant in the solar system's ongoing dance of matter and energy. The overnight color shift that first caught astronomers' attention represents only the beginning of a complex sequence of changes that will continue to challenge theoretical understanding and reveal new aspects of cometary physics. The mystery of why this particular comet activated so rapidly and dramatically remains unsolved, adding another puzzle to the growing collection of questions that make 3 I/Atlas one of the most scientifically intriguing visitors to grace our cosmic neighborhood in recent memory. Beneath the surface of 3 I/Atlas, molecular choreography unfolds with the precision of atomic clockwork. Sublimation, the direct transition from solid to gas that bypasses the liquid phase entirely, drives the comet's transformation through processes that operate at the boundary between thermodynamics and quantum mechanics. in the vacuum of space, where atmospheric pressure cannot exist. Ice crystals surrender their molecular constituents one by one, each departure governed by the balance between thermal energy and intermolecular forces that have held these structures intact for billions of years. The sublimation process begins when solar photons penetrate the nucleus surface and transfer their energy to the crystalline lattice. Individual molecules begin to vibrate with increasing amplitude as their thermal energy approaches the binding energy that holds them within the solid structure. At the critical threshold, a molecule breaks free from its crystalline constraints and enters the gas phase, carrying with it kinetic energy that propels it away from the nucleus at velocities measured in hundreds of meters per second. This molecular exodus creates the expanding envelope of gas that transforms the comet from a simple reflector of sunlight into an active source of characteristic emissions. Water molecules dominate the early stages of outgassing, their abundance reflecting the primordial composition of the outer solar nebula, where hydrogen and oxygen combined to form the most stable molecular configuration possible under those conditions. As H2O molecules escape the nucleus, they encounter the harsh environment of interplanetary space, where solar ultraviolet radiation immediately begins the process of photodissociation. The UV photons break the molecular bonds, splitting water into hydrogen atoms and hydroxyl radicals, OH, that contribute their own emission lines to the comet's evolving spectrum. Carbon monoxide presents a more volatile companion to the water ice, subliming at temperatures where water remains solidly frozen. CO molecules trapped within the water-ice matrix escape preferentially during the early stages of activation, their lower sublimation temperature making them among the first gases to contribute to the comet's brightening. The liberation of carbon monoxide creates an interesting chemical environment within the expanding coma, where CO molecules can react with other species to form more complex carbon-bearing compounds that contribute to the characteristic blue-green coloration observers detect from Earth. Nitrogen. Present in both molecular form, N2, and incorporated into more complex compounds like hydrogen cyanide, HCN, adds another layer of complexity to the sublimation chemistry. Molecular nitrogen proves particularly challenging to detect directly due to its chemical inertness and lack of strong spectral features in visible light, but its presence becomes apparent through secondary reactions and the formation of nitrogen-bearing radicals that do produce detectable emissions. The HCN component provides a more accessible tracer of nitrogen chemistry, breaking apart under solar radiation to produce the CN radicals that contribute distinctive spectral lines to cometary observations. The crystalline structure of the ice itself influences the sublimation process in ways that remain incompletely understood. Amorphous ice, formed through rapid cooling in the outer reaches of the solar nebula, possesses a different molecular arrangement than crystalline ice, with implications for how readily molecules can escape the solid matrix. As solar heating penetrates the nucleus, amorphous ice undergoes phase transitions that release stored energy, potentially contributing to the comet's unexpectedly rapid activation. This crystallization energy adds to the thermal budget available for sublimation, creating feedback loops that can accelerate outgassing beyond rates predicted by solar heating alone. Trace gases embedded within the major ice components contribute disproportionately to the comet's spectroscopic signature. Methane, ammonia, and various organic compounds present in minute concentrations produce emission lines that dominate certain portions of the spectrum despite their low abundance. These minority species often prove most valuable for understanding the comet's formation environment, as their presence requires specific temperature and chemical conditions that constrain models of early solar system evolution. The detection of complex organic molecules in cometary spectra has profound implications for understanding the distribution of prebiotic chemistry throughout the cosmos. The sublimation process creates its own microenvironment of chemical reactions within the expanding gas cloud, Freed molecules collide with each other and with solar photons, creating a cascade of secondary reactions that can produce species not originally present in the solid nucleus. These reaction products contribute new emission lines to the comet's spectrum and create chemical gradients within the coma that vary with distance from the nucleus. The chemistry becomes increasingly complex as more molecular species join the gas phase, creating a dynamic system that evolves continuously as the comet approaches the Sun. Temperature variations across the nucleus surface create non-uniform sublimation patterns that manifest as brightness variations and spectral changes correlated with the comet's rotation period. Areas directly illuminated by the Sun experience maximum heating and vigorous outgassing, while shadowed regions remain nearly inactive. The boundary between illuminated and dark areas creates steep temperature gradients that drive lateral gas flow along the surface, potentially transporting volatile materials from active to inactive regions through subsurface migration. This process redistributes the nucleus composition over time, gradually altering the comet's structure and outgassing characteristics. The liberation of dust particles embedded within the subliming ice adds a solid component to the expanding coma that interacts with the gas phase through collisional processes. These dust grains, ranging in size from nanometers to micrometers, become entrained in the outflowing gas and carry with them information about the solid material present in the original nucleus. The dust-gas interaction creates drag forces that influence the dynamics of both components, while radiative heating of the dust particles creates infrared emission that contributes to the comet's thermal signature. Isotopic fractionation during sublimation provides subtle but important information about the physical conditions within the nucleus. Heavier isotopes of hydrogen, carbon, nitrogen, and oxygen sublime at slightly different rates than their lighter counterparts, creating isotopic signatures in the escaping gases that reflect both the original composition of the nucleus and the conditions under which sublimation occurs. These isotopic ratios serve as fingerprints that can reveal the comet's formation location within the early solar system and the processes that governed its subsequent evolution. The expanding gas cloud begins to interact with the solar wind. Charged particles streaming outward from the Sun at velocities of several hundred kilometers per second. This interaction creates the first stirrings of electromagnetic activity around the comet as ionized gas molecules respond to magnetic fields carried by the solar wind. The process remains subtle at 3 I/Atlas's current distance from the Sun, but it represents the beginning of more dramatic phenomena that will develop as the comet continues its inward journey. The gentle chemistry of sublimation thus opens the door to the more energetic physics of plasma interactions that will eventually sculpt the comet's magnificent tail and create some of the solar system's most spectacular displays of matter and energy in motion. Within the subliming ice matrix of 3 I/Atlas, countless dust grains await their liberation like seeds embedded in dissolving earth. These microscopic particles, each smaller than the wavelength of visible light, represent the solid remnants of processes that occurred before the solar system existed, fragments of interstellar dust that served as condensation nuclei when the comet first accreted from the primordial nebula. Now, as the surrounding ice transforms from solid to gas, these ancient travelers begin their own journey into the vacuum of space, carrying with them the chemical and physical record of cosmic processes that stretch back billions of years. The dust particles emerge from their icy prison through a process of gentle excavation rather than violent ejection, as water, carbon monoxide, and other volatile species sublime away. They leave behind a delicate scaffolding of solid material that has no independent structural strength in the absence of the binding ice. Surface tension forces, negligible in terrestrial environments, but significant at microscopic scales, initially hold the particles together in fragile aggregates. These loosely bound clusters begin to disintegrate as thermal cycling and gas flow stress their tenuous connections, releasing individual grains into the expanding coma one by one. Each liberated particle carries within its atomic structure the signature of its formation environment. Silicate grains, composed primarily of silicon, magnesium, and iron combined with oxygen, preserve isotopic ratios that reflect nucleosynthesis processes in the massive stars that forge these elements through fusion reactions and explosive supernovae. The silicon isotopes reveal the temperature and density conditions within stellar cores, while iron isotope ratios provide information about the neutron flux environments that characterize the final moments of stellar collapse. These particles have wandered through the interstellar space for millions of years before being incorporated into the growing comet nucleus. Carbonaceous particles tell a different story of organic chemistry that occurred in the cold, dense regions of interstellar space. These grains contain complex hydrocarbon molecules formed through surface reactions on dust particles exposed to cosmic radiation and the ultraviolet light of distant stars. The carbon-bearing compounds include polycyclic aromatic hydrocarbons, long-chain aliphatic molecules, and nitrogen-bearing heterocycles that represent some of the most complex organic chemistry known to occur naturally in space. The preservation of these molecules within the comet nucleus provides a direct sample of the prebiotic organic chemistry that existed before planets formed. The liberation process imparts specific velocities to the dust particles based on their size, mass, and the local gas flow conditions at the point of release. Smaller particles, with higher surface area to mass ratios, couple more efficiently to the expanding gas flow and achieve higher velocities relative to the nucleus. Larger particles, less influenced by gas drag, move more slowly and tend to remain closer to the comet as the gas expands outward. This size-dependent sorting creates a spatial gradient of particle sizes within the developing coma, with the finest dust forming an extended envelope while larger particles concentrate near the nucleus. Optical properties of the dust particles determine how they interact with solar radiation once liberated from the nucleus. The particles absorb solar energy across a broad spectrum of wavelengths, converting photon energy into thermal motion that raises their temperature above the surrounding gas. This heating drives secondary sublimation processes as any remaining ice mantles on the particle surfaces begin to sublime, contributing additional gas to the coma and potentially fragmenting particles that contain internal ice inclusions. The thermal emission from heated dust particles creates the infrared signature that allows astronomers to study the solid component of cometary composition. The dust particles exhibit a range of compositions that reflects the heterogeneous nature of the interstellar medium from which the comet formed. Pure silicate grains, composed of olivine and pyroxene minerals familiar from meteorite studies, represent condensation from high-temperature stellar environments. Iron-nickel particles preserve samples of metallic phases that formed in the cores of differentiated asteroids disrupted by collisions. Organic particles contain the complex carbon chemistry of cold molecular clouds, while composite particles combine multiple phases into single grains that recorded multiple episodes of processing in different cosmic environments. Electromagnetic properties of the dust become important as the particles enter the realm of solar-wind interaction. Many dust particles carry electric charges acquired through various mechanisms, including photoelectron emission, impact by solar wind particles, and secondary electron emission from cosmic ray bombardment. These charged particles respond to magnetic fields carried by the solar wind, creating complex trajectories that deviate from simple ballistic paths. The electromagnetic forces become increasingly important as 3I/Atlas approaches the Sun and the solar wind. Intensity increases. Size distribution of the liberated dust follows a power law relationship that reflects the fractal nature of grain growth processes in the early solar system. The majority of particles fall within the submicron size range, though a smaller population of larger particles extends the distribution to sizes approaching several micrometers. This size spectrum influences how the dust interacts with solar radiation, with different sized particles contributing different scattering and thermal emission characteristics to the comet's overall optical signature. The size distribution also determines how effectively the particles couple to gas flow and electromagnetic forces. Crystalline structure analysis of individual particles, possible through advanced laboratory techniques applied to collected samples, reveals the thermal history experienced by these grains since their formation. Some particles preserve amorphous structures that indicate formation in low-temperature environments and subsequent preservation in the cold of space. Others show evidence of thermal processing that created crystalline mineral phases, suggesting exposure to heat sources during their journey through the interstellar medium or during the early stages of solar system formation. The liberation of dust particles from 3y/Atlas creates a population of interplanetary debris that will continue to orbit the Sun long after the comet has passed perihelion and retreated to the outer solar system. These particles gradually spiral inward toward the Sun through the Poynting-Robertson effect, a subtle radiation pressure phenomenon that causes small particles to lose orbital energy and eventually fall into the solar photosphere. The process takes millions of years for typical cometary dust particles, creating a long-lived record of the comet's passage that persists in the form of scattered debris distributed throughout the inner solar system. Chemical analysis of the dust composition provides direct information about pre-solar materials that existed before the solar system formed. Isotopic anomalies in individual particles reveal their origin in specific stellar environments, allowing researchers to trace the sources of different elements incorporated into the solar nebula. The preservation of these signatures within cometary dust makes objects like 3I/Atlas invaluable for understanding the galactic chemical evolution that led to the formation of our solar system, and the complex mixture of elements that made planetary formation possible. The gentle process of dust grain liberation thus represents more than simply the mechanical release of solid particles from a subliming ice matrix. Each grain carries with it a fragment of cosmic history, preserving information about stellar nucleosynthesis, interstellar chemistry, and early solar system processes in forms that remain accessible to scientific investigation billions of years after their formation. The dust of 3I/Atlas connects the present moment to the deep past of our galaxy, carrying messages written in atomic nuclei and molecular structures that tell the story of how elements forged in stellar cores eventually found their way into the small, cold world, now awakening to the warmth of our Sun. Around the slowly tumbling nucleus of 3I/Atlas, an invisible transformation unfolds with the patience of cosmic processes. The expanding coma grows larger with each passing hour, its boundaries defined not by any physical surface, but by the gradually decreasing density of gas and dust molecules spreading outward from their source. This gossamer envelope, transparent to human eyes yet dense enough to scatter and absorb specific wavelengths of solar radiation, represents the comet's first tentative reach into the space around it, transforming 3I/Atlas from a simple point of reflected light into an extended object with measurable structure and complexity. The coma expansion follows the fundamental physics of gas dynamics in a vacuum, where molecules released from the nucleus surface travel in straight lines until they encounter other particles or electromagnetic forces. The initial velocity of escaping molecules, determined by the balance between thermal energy and the gravitational attraction of the nucleus, creates an expanding sphere of material that grows at a rate measured in hundreds of meters per second. This velocity, modest by astronomical standards, proves sufficient to overcome the weak gravitational field of the small nucleus and carry the liberated gases into interplanetary space. Temperature gradients within the expanding gas create subtle variations in molecular velocities that influence the coma's internal structure. Molecules released from the warmest regions of the nucleus carry more kinetic energy and travel faster than those escaping from cooler areas, creating velocity distributions that reflect the thermal environment at the point of release. These velocity differences manifest as density variations within the coma, with faster-moving molecules creating lower density regions at greater distances from the nucleus, while slower molecules remain concentrated closer to the source. The spherical symmetry expected from simple gas expansion becomes modified by the nucleus rotation and non-uniform surface activity, as different regions of the irregular nucleus face the Sun during each rotation cycle. The pattern of outgassing changes correspondingly, creating time-variable source functions that inject gas into the coma with directional preferences. This temporal modulation imprints the nucleus rotation period onto the coma structure, creating subtle spiral patterns within the gas distribution that reflect the interplay between rotation and radial expansion. Collisional processes within the inner regions of the coma influence the trajectories of newly released molecules before they enter the collisionless regime of free expansion. Near the nucleus surface, where gas density remains relatively high, molecules undergo multiple collisions with each other before escaping to larger distances. These collisions redistribute kinetic energy among different molecular species and create a partially thermalized velocity distribution that differs from the initial conditions at the point of sublimation. The collisional zone extends outward from the nucleus surface for distances that depend on the local gas production rate and the cross-sections for molecular collisions. Different molecular species within the coma exhibit varying degrees of photodissociation as they encounter solar ultraviolet radiation. Water molecules, the most abundant constituent, break apart to form hydrogen atoms and hydroxyl radicals at rates determined by the intensity of UV radiation and the molecular absorption cross-sections. This photochemical processing creates daughter products that were not originally present in the nucleus, adding new spectral features to the comet's emission signature and creating chemical gradients within the coma that vary with distance from the nucleus. The hydroxyl radicals produced by water photodissociation become particularly important for ground-based observations due to their strong emission lines in the optical wavelength range. These OH radicals fluoresce when excited by solar radiation, producing characteristic emission features that dominate the comet's spectrum and contribute significantly to its overall brightness. The spatial distribution of OH emission within the coma provides information about the water production rate and the efficiency of photodissociation processes occurring in the expanding gas cloud. Carbon-bearing molecules contribute the distinctive blue-green coloration that makes active comets visually striking objects. Diatomic carbon, C2, and the cyanogen radical, Cn, produce strong emission lines in the blue and violet portions of the spectrum when excited by solar ultraviolet radiation. These molecules, formed through photodissociation of more complex parent species within the nucleus, create emission features that can be detected even when the comet appears as nothing more than a fuzzy star through small telescopes. The intensity of these emissions provides direct information about the production rates of carbon-bearing compounds from the nucleus. Dust particles liberated along with the gas create additional complexity within the coma through their interaction with solar radiation. The particles absorb solar energy and re-emit it as thermal radiation in the infrared wavelength range, contributing to the comet's thermal signature and providing information about the composition and size distribution of solid materials within the nucleus. The dust also scatters solar radiation, creating a continuum background upon which the discrete emission lines from gas species are superimposed. The expansion velocity of the coma creates Doppler shifts in the emission lines that can be measured spectroscopically. Gas moving toward Earth appears slightly blue-shifted in wavelength, while gas moving away appears red-shifted, creating characteristic line profiles that reveal information about the three-dimensional structure of the expanding envelope. These Doppler measurements provide direct evidence for the radial expansion of the coma and allow researchers to determine the velocity field within the gas cloud. Temporal variations in the coma brightness and structure reflect changes in the nucleus activity as different surface regions rotate into and out of solar illumination. The photometric monitoring reveals periodicities that correspond to the nucleus rotation period, providing information about the distribution of active areas on the surface and the degree of heterogeneity in surface composition. These rotation-induced variations create a complex interplay between the slowly changing orbital geometry and the rapidly varying local solar illumination conditions. The invisible nature of most coma structure to visual observation makes 3E/Atlas appear deceptively simple through small telescopes, where it resembles nothing more than a slightly fuzzy star moving slowly against the stellar background. Only through photographic techniques, spectroscopic analysis, and careful photometric measurements does the complexity of the expanding gas and dust envelope become apparent. The coma represents one of astronomy's most beautiful examples of how invisible processes can create profound changes in observable properties, transforming a simple reflected light object into an active source of characteristic emissions that encode information about fundamental physical and chemical processes. Radio observations reveal additional aspects of coma structure through the detection of molecular transitions that occur in the microwave portion of the electromagnetic spectrum. These observations probe different physical conditions within the coma and provide complementary information about molecular abundances, temperatures, and kinetic processes that influence the evolution of the expanding gas cloud. The radio signatures of cometary molecules become increasingly important for understanding the detailed physics and chemistry of coma environments. As the sixth section of 3I/Atlas's story concludes, the expanding coma continues its silent growth, creating an invisible atmosphere around the nucleus that transforms the comet's interaction with its space environment. The gossamer envelope remains transparent and tenuous by terrestrial standards, yet it fundamentally alters the comet's optical properties and creates the conditions necessary for the more dramatic phenomena that will develop as the journey toward the Sun continues. In the vast emptiness of the outer solar system, this gentle expansion of gas and dust represents the comet's first step toward becoming one of nature's most spectacular displays of matter and energy in motion. From the Sun streams an invisible river of charged particles, flowing outward through the solar system at velocities that dwarf the motion of planets and comets. This solar wind, composed primarily of protons and electrons, accelerated to hundreds of kilometers per second by processes occurring in the solar corona, carries with it magnetic field lines that thread through interplanetary space, like gossamer strands of electromagnetic influence. As 3I/Atlas continues its inward journey, its expanding coma begins to encounter this stellar breath for the first time in its long existence, initiating interactions that will gradually transform the comet from a simple source of neutral gas into a complex plasma physics laboratory suspended in the vacuum of space. The initial contact between the comet's neutral gas envelope and the solar wind occurs through a process of gradual pressure equilibrium rather than dramatic collision. The solar wind exerts dynamic pressure on any obstacle in its path, creating disturbances in the flow pattern that extend far beyond the physical size of the obstruction. Around 3I/Atlas, this pressure begins to compress the expanding coma, creating the first deviation from perfectly radial gas flow as the outward motion of neutral molecules encounters the gentle but persistent push of the streaming plasma. Within the coma, individual gas molecules begin to experience ionization as high-energy solar wind particles and solar ultraviolet photons strip away electrons from neutral atoms and molecules. This ionization process creates a population of charged particles within the previously neutral gas cloud, transforming water molecules into H2O+ ions, carbon monoxide into CO+ ions, and creating a variety of molecular ions that respond to electromagnetic forces in ways their neutral parent molecules cannot. The ionization occurs gradually, creating spatial gradients of ionization fraction that vary with distance from the nucleus and exposure time to the ionizing radiation. The newly created ions immediately begin to interact with the magnetic field carried by the solar wind, a process that fundamentally alters their trajectories from the simple radial expansion characteristic of neutral gas. Charged particles experience forces perpendicular to both their velocity and the local magnetic field direction, causing them to spiral around magnetic field lines in helical paths. This electromagnetic interaction creates the first stirrings of what will eventually become the comet's ion tail, as charged particles begin to deviate from radial outflow and align themselves with the direction of the solar wind flow. The magnetic field interaction also creates electrical currents within the ionized portion of the coma, as moving charges respond to the electromagnetic environment. These currents, though extremely weak by terrestrial standards, represent the beginning of a complex system of plasma physics phenomena that will intensify as 3I/8 approaches the Sun and its gas production increases. The current systems create their own magnetic fields that interact with the solar wind field, establishing feedback loops that influence the structure and dynamics of the expanding gas envelope. Electron impact ionization provides an additional mechanism for creating charged particles within the coma, as high-energy electrons in the solar wind collide with neutral molecules and transfer sufficient energy to remove bound electrons. This process occurs more readily with some molecular species than others, creating selective ionization patterns that depend on the ionization potentials of different molecules. Water molecules, with their relatively high ionization potential, ionize less readily than carbon monoxide or atomic hydrogen, creating compositional variations within the ionized component of the coma. The pressure exerted by the solar wind creates a standoff distance around the comet where the outward flow of neutral gas balances the inward pressure of the streaming plasma. This interaction region, though invisible to optical observation, represents the first formation of what plasma physicists call a cometary magnetosphere, a region of space where the comet's gas production influences the local electromagnetic environment. The standoff distance varies with both the gas production rate from the nucleus and the dynamic pressure of the solar wind, creating a time-variable boundary that responds to changes in both the comet's activity and solar wind conditions. Charge exchange reactions between solar wind ions and neutral coma molecules create energetic neutral atoms that carry information about the solar wind composition and velocity. When a high-velocity solar wind proton captures an electron from a slow-moving water molecule, the resulting neutral hydrogen atom retains most of the original proton's kinetic energy, while the water molecule becomes ionized. These energetic neutral atoms travel in straight lines unaffected by magnetic fields, creating a population of high-velocity particles within the coma that provides information about local solar wind conditions. The gentle pressure of solar wind interaction begins to create asymmetries in the coma structure as gas flowing in the anti-solar direction encounters less resistance than gas moving toward the Sun. This pressure gradient creates the first hint of directional structure within what was previously a spherically symmetric expansion, pointing toward the dramatic tail formation that will characterize the comet's appearance as it continues its approach to the inner solar system. The asymmetry remains subtle at 3y/Atlas's current distance, but represents the beginning of the process that creates the spectacular comet tails visible to terrestrial observers. Plasma instabilities within the interaction region create small-scale turbulence that influences the mixing and transport of different ionic species. These instabilities, driven by gradients in density, temperature, and magnetic field strength, create fluctuations in the electromagnetic environment that affect the trajectories of individual charged particles. The turbulent processes contribute to heating of the plasma component and influence the efficiency of various ionization and recombination processes occurring within the coma. The solar-wind interaction also influences the escape rate of neutral molecules from the nucleus by creating pressure variations that affect the expansion velocity of the gas flow. Higher solar wind pressure tends to compress the inner coma and increase the local gas density, which can influence collisional processes and alter the temperature distribution within the gas cloud. These feedback effects create coupling between the external solar wind environment and the internal processes occurring within the nucleus and inner coma. Radio emission at very low frequencies begins to develop as charged particles accelerated by electromagnetic forces create current fluctuations that radiate electromagnetic energy. These emissions, too weak and too low in frequency to be detected by ground-based instruments, represent the first stirrings of the radio phenomena that will become more prominent as the comet's plasma environment develops. The radio signatures provide information about electron densities, magnetic field strengths, and wave-particle interactions occurring within the comet's electromagnetic environment. Temporal variations in solar wind properties create corresponding changes in the comet's plasma environment, as variations in solar wind velocity, density, and magnetic field strength propagate outward from the Sun and encounter the expanding coma. These variations, caused by solar activity such as coronal mass ejections and solar flares, create a dynamic interaction environment that responds to conditions on the solar surface days or weeks earlier. The comet thus becomes a remote sensor of solar activity, its plasma properties reflecting the variable nature of our star's electromagnetic output. The gentle pressure of the solar wind represents the first of many electromagnetic phenomena that will increasingly dominate 3Y/Atlas's behavior as it continues its inward journey. The subtle effects occurring at the comet's current distance from the Sun will amplify and intensify, eventually creating some of the solar system's most dramatic displays of plasma physics in action. For now, the interaction remains gentle and largely invisible. A quiet beginning to the complex electromagnetic dance that will transform this ancient wanderer into one of nature's most spectacular demonstrations of matter and energy in motion through the vast emptiness of interplanetary space. Ground-based observatories around the world train their instruments on the brightening speck of light that has become 3E/8less, their sensitive detectors capturing photons that have traveled across millions of kilometers of space to tell the story of molecular transformations occurring within the comet's expanding coma. The spectroscopic analysis reveals a chemical complexity that challenges existing models of cometary composition. As emission lines appear in the comet's spectrum that correspond to molecular species not typically observed at such distances from the Sun. These unexpected signatures hint at internal processes within the nucleus that operate according to principles not yet fully understood by cometary science. The most puzzling aspect of the spectroscopic observations lies in the presence of complex organic molecules that should not survive the harsh radiation environment of interplanetary space, polyatomic carbon chains. Detected through their characteristic emission features in the near-infrared portion of the spectrum, suggests that the nucleus contains organic compounds of greater complexity than the simple molecules typically associated with cometary outgassing. The survival of these fragile molecular structures implies either exceptional preservation conditions within the nucleus or active formation processes that create new organic compounds as the comet approaches the Sun. Isotopic analysis of the molecular emissions provides additional evidence for the unusual nature of 3Y/Atlas's composition. The ratio of deuterium to hydrogen in water molecules shows significant enhancement compared to terrestrial values, indicating formation in extremely cold conditions where deuterium fractionation processes could operate efficiently. This isotopic signature points toward origin in the outermost regions of the solar nebula or incorporation of interstellar ice that formed in molecular clouds with temperatures near absolute zero. The deuterium enhancement exceeds values observed in most other comets, suggesting a formation environment even more remote and pristine than typical cometary birth regions. Carbon isotope ratios reveal further anomalies that complicate attempts to understand the comet's origin and evolution. The ratio of carbon-13 to carbon-12 in carbon monoxide and other carbon-bearing molecules shows variations that cannot be explained by standard models of isotopic fractionation in the early solar system. Some molecular species show carbon-13 enhancement, while others appear depleted, creating a patchwork of isotopic signatures that suggests multiple sources of carbon incorporated into the nucleus during its formation. These variations might reflect the mixing of materials from different regions of the early solar system or the incorporation of pre-solar grains with diverse stellar origins. Nitrogen isotope measurements add another layer of complexity to the chemical puzzle presented by 3I/Atlas. The ratio of nitrogen-15 to nitrogen-14 in hydrogen cyanide and other nitrogen-bearing compounds shows extreme enrichment in the heavy isotope, values that exceed even the most anomalous measurements from other comets and approach the compositions observed in some interstellar molecules. This nitrogen isotopic signature suggests formation processes that operated under conditions of extreme cold and low density, possibly in the outer regions of the solar nebula where temperatures remained below 30 Kelvin throughout the accretion period. Oxygen isotope analysis reveals triple isotope effects that provide additional constraints on formation conditions and subsequent thermal processing. The relationship between oxygen-16, oxygen-17, and oxygen-18 abundances in water and carbon monoxide shows patterns consistent with low-temperature chemical processes that occurred in the presence of atomic oxygen generated by photodissociation of carbon monoxide. These oxygen isotope signatures preserve information about the irradiation environment during the comet's formation, suggesting exposure to ultraviolet radiation from nearby massive stars that influence the chemistry of the forming nucleus. Trace element detection through high-resolution spectroscopy reveals the presence of metallic species that provide information about the refractory component of the nucleus composition. Sodium, iron, and magnesium emissions appear in the comet's spectrum with intensities that suggest the presence of metallic particles within the subliming ice matrix. The relative abundances of these elements match the solar composition more closely than typical meteoritic materials, indicating that the refractory component of 3Y/Atlas represents relatively unprocessed samples of early solar system condensates. The temporal evolution of molecular emission lines provides insights into the internal structure and composition gradients within the nucleus. As solar heating penetrates deeper into the comet's interior, different molecular species appear in the spectrum with timing that reflects their depth of burial within the original ice matrix. The earliest emissions come from the most volatile species concentrated near the surface, followed by water and other moderately volatile compounds, and finally by more refractory materials embedded in the nucleus interior. This sequence of molecular appearances creates a stratigraphic record of the comet's accretion history. Radio observations of molecular transitions provide complementary information about physical conditions within the coma that cannot be obtained through optical spectroscopy. The rotational transitions of carbon monoxide, hydrogen cyanide, and other molecules occur at millimeter wavelengths where atmospheric transmission allows ground-based observation of these weak signals. The radio measurements reveal gas temperatures, molecular abundances, and kinetic processes that influence the expansion dynamics of the coma and provide constraints on models of cometary outgassing. Polarization measurements of scattered light from dust particles within the coma reveal compositional information about the solid component of the nucleus. The degree and orientation of linear polarization depend on the size, shape, and refractive properties of the scattering particles, providing constraints on the mineralogy and structure of dust grains embedded within the subliming ice. The polarization signature of 3Y/Atlas matches most closely with carbonaceous materials mixed with silicate minerals, in proportions that reflect the composition of the most primitive meteorites. Spatial distribution of different molecular species within the expanding coma creates a three-dimensional chemical map that reveals information about outgassing patterns and photochemical processing. Parent molecules released directly from the nucleus show different spatial distributions than daughter products created by photodissociation, allowing researchers to trace the chemical evolution of the gas cloud as it expands away from the source. These spatial variations also reveal information about the heterogeneity of nucleus composition and the locations of active regions on the surface. The mystery of 3I/Atlas's unusual chemical composition deepens with each new observation, as additional molecular species appear in the spectrum that have never been detected in cometary environments. Complex hydrocarbons, nitrogen-bearing heterocycles, and sulfur-containing compounds contribute emission features that require revision of existing models of cometary chemistry. The detection of these unexpected molecular species suggests that comets may preserve a much richer inventory of organic chemistry than previously recognized, with implications for understanding the role of comets in delivering complex organic compounds to the early Earth. Comparison with other comets observed under similar conditions reveals that 3I/Atlas represents an extreme example of chemical complexity within the cometary population. While all comets show some degree of compositional variation that reflects their formation environments and subsequent evolution, the molecular inventory of 3I/Atlas exceeds the diversity observed in any previously studied comet. This exceptional chemical richness makes the comet particularly valuable for understanding the full range of compositions present within the comet population and the processes that governed chemical evolution in the early solar system. The spectroscopic mysteries presented by 3I/Atlas continue to challenge theoretical understanding as new observations reveal additional layers of chemical complexity within the awakening nucleus. Each new molecular detection adds another piece to the puzzle of how this ancient time capsule preserved such a rich chemical heritage through billions of years of cosmic wandering, and what processes now drive its transformation from dormant wanderer to active participant in the ongoing chemical evolution of the solar system. Beneath the expanding veil of gas and dust that shrouds 3I/Atlas, the comet's solid heart reveals itself through the patient application of radar astronomy techniques that penetrate the obscuring coma to map the hidden landscape of the nucleus itself. Radio telescopes on Earth transmit powerful signals across the void, their electromagnetic pulses racing outward at the speed of light to encounter the tumbling nucleus and reflect back with information encoded in the subtle changes of frequency, polarization, and time delay that characterize the radar echo. These reflected signals carry within their electromagnetic structure a detailed portrait of the nucleus surface and interior, revealing topographic features, composition variations, and rotational dynamics that remain invisible to optical observation. The nucleus emerges from radar analysis as an irregularly shaped object approximately 2 kilometers in its longest dimension, with a complex surface topography that speaks to billions of years of evolutionary processes. Impact craters of various sizes pit the surface, their circular rims and central peaks preserved in the radar imagery like fossil records of ancient collisions with asteroids and meteoroids. The largest crater, nearly 400 meters across, dominates one hemisphere of the nucleus and suggests a catastrophic impact event that occurred early in the comet's history, when debris from planetary formation still populated the outer solar system in greater abundance than today. Smooth, relatively flat regions alternate with areas of rugged terrain that exhibit the characteristic signatures of sublimation erosion. These smoother areas represent zones where volatile materials have sublimed away preferentially, leaving behind lag deposits of non-volatile dust and rock that create a protective mantle over the underlying ice. The radar reflectivity of these regions indicates compositions dominated by carbonaceous materials mixed with silicate minerals, creating surfaces darker than charcoal that absorb solar radiation efficiently and contribute to the thermal processes driving continued outgassing from adjacent areas. Active regions on the nucleus surface reveal themselves through radar analysis as areas of enhanced backscatter that indicate rough, freshly exposed surfaces where sublimation actively erodes the nucleus structure. These regions, comprising perhaps 10% of the total surface area, show radar characteristics consistent with clean ice mixed with entrained dust particles. The spatial correlation between these radar-bright regions and the sources of gas jets detected in optical observations confirms that sublimation occurs preferentially from localized areas rather than uniformly across the entire nucleus surface. The internal structure of the nucleus, probed through analysis of radar signal penetration and reflection characteristics, suggests a heterogeneous interior with variations in density and composition that reflect the accretion history of the object. Radar waves penetrate several meters into the nucleus before encountering interfaces between materials of different dielectric properties, revealing a layered structure that might record episodic accretion events during the comet's formation. These internal boundaries create secondary radar reflections that arrive at Earth with time delays that map the three-dimensional structure hidden beneath the surface. Density measurements derived from the radar data, combined with gravitational perturbation analysis of gas and dust trajectories, indicate that the nucleus possesses an overall density significantly lower than solid ice, suggesting a highly porous internal structure. This porosity, estimated at 70% by volume, implies that the nucleus resembles a loosely consolidated rubble pile held together primarily by gravitational forces and weak cohesive interactions between constituent particles. The porous structure provides pathways for gas flow within the nucleus interior and creates reservoirs where volatile materials can accumulate and sublime in response to thermal cycling. Rotational analysis reveals that 3I/Atlas tumbles in a complex, non-principal axis rotation state that indicates the nucleus is not in hydrostatic equilibrium. The rotation period varies slightly over time scales of days to weeks as internal mass redistribution and outgassing torques influence the angular momentum distribution within the irregularly shaped body. This non-principal axis rotation, also observed in several asteroids and other comets, suggests that the nucleus experienced impacts or other perturbations that altered its rotational state from the simple spinning motion expected for objects in rotational equilibrium. Surface roughness measurements at various scales reveal a fractal texture that extends from kilometer-scale topographic features down to the resolution limit of the radar observations at meter scales. This scale-invariant roughness suggests that similar physical processes operate across multiple size scales to create surface texture, possibly including impact cratering, sublimation erosion, and thermal fracturing processes that each contribute to the overall surface morphology. The fractal nature of the surface texture influences how solar radiation is absorbed and scattered, affecting the thermal environment that drives sublimation processes. Thermal inertia measurements, derived from the correlation between radar reflectivity and thermal emission characteristics, indicate that surface materials possess extremely low thermal conductivity values typical of unconsolidated dust layers. This low thermal inertia suggests that diurnal temperature variations penetrate only centimeters into the surface, creating steep thermal gradients that influence sublimation patterns and stress the surface materials through repeated thermal cycling. The thermal properties vary across the nucleus surface, with active regions showing higher thermal inertia consistent with more consolidated surface materials. Subsurface layering detected through radar penetration studies reveals stratification within the nucleus that might record variations in accretion conditions during the comet's formation. Individual layers, ranging from meters to tens of meters in thickness, show different radar reflection characteristics that suggest compositional or textural variations. These layers might represent episodic accretion events, periods of different chemical conditions in the early solar nebula, or post-formation processes such as impact gardening that have redistributed materials within the nucleus interior. The radar observations also detect evidence for internal voids or cavities within the nucleus structure, regions of extremely low radar reflectivity that suggest empty spaces carved out by sublimation processes or representing original porosity from the accretion process. These voids, ranging from meters to tens of meters in size, provide pathways for gas migration within the nucleus and create structural weaknesses that might influence how the nucleus responds to thermal stresses and rotational forces as it continues its approach toward the Sun. Compositional mapping through polarimetric radar analysis reveals heterogeneity in the electrical properties of surface materials that correlates with variations in outgassing activity. Regions with high radar circular polarization ratios suggest the presence of pristine ice or highly reflective materials, while areas with low polarization ratios indicate surfaces dominated by absorbing materials such as organic compounds or metal-bearing minerals. This compositional heterogeneity reflects the complex accretion history of the nucleus and provides insight into the spatial distribution of volatile and refractory materials within the comet. Surface evolution processes, inferred from the correlation between topographic features and outgassing patterns, indicate that the nucleus undergoes continuous modification as sublimation erodes some regions while depositing non-volatile lag materials in others. The most active sublimation regions tend to occur in topographic lows where solar radiation can be focused by reflection from surrounding slopes, creating thermal concentration effects that enhance local heating. Conversely, shadowed regions and areas covered by thick lag deposits show minimal current activity despite potentially containing substantial volatile reserves beneath the surface. The detailed portrait of the nucleus revealed through radar observations transforms 3I/Atlas from an abstract point of light into a complex, geologically active world with its own landscape of mountains, valleys, and plains sculpted by billions of years of cosmic processes. This hidden geography, invisible to optical telescopes but accessible through the penetrating power of radio waves, provides the foundation for understanding how this ancient time capsule responds to the increasing warmth of solar heating as it continues its journey toward the inner solar system. The nucleus of 3I/Atlas completes one full rotation every 7 hours, its irregular shape creating a complex thermal environment where temperature variations drive intricate patterns of sublimation and recondensation across its surface. As different regions rotate into and out of solar illumination, the comet experiences a rapid succession of local seasons that compress the thermal cycles of planetary worlds into time frames measured in hours rather than months or years. This accelerated day-night rhythm creates temperature gradients steep enough to fracture rock and sublimate ice, yet gentle enough to preserve delicate crystal structures that have remained unchanged for billions of years. During the comet's local noon, when a given surface element faces the Sun most directly, temperatures rise from the baseline cold of space to values that can reach 180 Kelvin, still far below the freezing point of water on Earth, yet warm enough to drive vigorous sublimation of the most volatile constituents embedded within the nucleus structure. Carbon monoxide ice begins to sublime actively at temperatures above 25 Kelvin, while water ice remains largely stable until temperatures exceed 150 Kelvin. This temperature-dependent sublimation creates a sequence of outgassing events as each surface region warms through its daily thermal cycle, contributing different molecular species to the expanding coma at different times. The thermal wave generated by solar heating penetrates into the nucleus interior at a rate determined by the thermal diffusivity of the constituent materials. In the loose, porous structure typical of cometary nuclei. Heat conduction occurs slowly, requiring hours for temperature changes to propagate even centimeters beneath the surface. This thermal lag means that subsurface temperatures continue to rise for hours after a surface region has rotated away from direct solar illumination, creating complex three-dimensional temperature distributions that drive internal gas flow and influence the mechanical properties of the nucleus structure. Sublimation cooling provides a natural thermostat that regulates surface temperatures in actively outgassing regions. As volatile materials absorb thermal energy to drive the phase transition from solid to gas, they remove heat from their immediate surroundings, preventing temperatures from rising as high as they would on an inactive surface. This cooling effect becomes particularly pronounced in regions with high concentrations of volatile materials, creating spatial variations in surface temperature that correlate with compositional heterogeneity across the nucleus. The irregular shape of the nucleus creates complex patterns of solar illumination that vary dramatically with rotational phase. Steep slopes facing the sun receive enhanced heating due to the concentrated solar flux, while nearby shadowed areas remain at temperatures close to the cosmic background. These illumination effects create local hotspots where thermal focusing concentrates solar energy, potentially driving enhanced sublimation from small areas that contribute disproportionately to the overall gas production. The interplay between topography and solar angle creates a shifting mosaic of thermal conditions that changes continuously as the nucleus rotates. Internal heat sources contribute additional complexity to the thermal environment within the nucleus. Radioactive decay of long-lived isotopes incorporated during the comet's formation provides a steady, if modest, source of thermal energy that operates independently of solar heating. Crystallization energy released as amorphous ice transitions to more stable crystalline forms adds episodic contributions to the internal thermal budget. These internal heat sources, though small compared to solar heating, can influence sublimation patterns and create thermal gradients that drive gas migration within the porous nucleus structure. The porous nature of the nucleus creates an internal atmosphere where gas molecules sublimed from internal ice deposits can migrate through interconnected void spaces before either recondensing on cooler surfaces or escaping to the external coma. This internal gas transport system allows volatile materials sublimed from one region to recondense in another, creating a slow redistribution of ice throughout the nucleus structure. The migration process operates on timescales much longer than the rotational period, gradually altering the internal composition distribution over multiple orbital passages around the Sun. Thermal stress fracturing occurs as temperature variations create differential expansion and contraction within the nucleus materials. The coefficient of thermal expansion for ice differs significantly from that of rocky materials, creating internal stresses at interfaces between different components. These stresses accumulate over repeated thermal cycles until they exceed the tensile strength of the materials, creating fractures that provide new pathways for gas escape and alter the mechanical structure of the nucleus. The fracturing process operates most effectively in regions experiencing the largest temperature variations. Recondensation processes become important in regions where sublimed gases encounter surfaces cooler than their saturation temperature. Water vapor migrating through the porous nucleus structure can recondense as frost on grain surfaces in shadowed or subsurface regions, while more volatile species like carbon monoxide may remain in the gas phase unless they encounter extremely cold surfaces. The recondensation process can create ice deposits in locations removed from the original sublimation sites, contributing to the internal redistribution of volatile materials. Seasonal effects related to the comet's orbital motion create longer-term variations in the thermal environment that modify the daily rotation cycles. As 3I/Atlas continues its approach toward the Sun, The baseline thermal environment gradually warms, allowing sublimation processes to penetrate deeper into the nucleus and activate previously dormant regions. This progressive activation creates a feedback loop where increased gas production enhances the comet's activity level and contributes to accelerating brightening as the orbital approach continues. The thermal inertia of different surface materials influences how rapidly temperatures respond to changes in solar illumination. Regions covered with fine dust particles heat and cool more rapidly than areas with larger rocky fragments or consolidated materials, creating temporal variations in outgassing that correlate with surface texture and composition. These thermal inertia effects contribute to the complex time-variable behavior observed in the comet's brightness and spectroscopic properties as different surface regions contribute to the overall activity level. Diurnal temperature variations create convective processes within the tenuous internal atmosphere of the nucleus, as heated gases rise through the porous structure while cooler gases settle into deeper regions. These convection patterns influence the transport of volatile materials within the nucleus and can concentrate certain molecular species in specific regions through gravitational settling and thermal diffusion processes. The convective transport operates slowly compared to the rotational period, but becomes significant over longer time scales. The coupling between thermal and mechanical processes creates complex feedback loops that influence the long-term evolution of the nucleus structure. Thermal expansion and contraction alter the porosity and permeability of the nucleus materials, affecting how efficiently heat can be conducted and how easily gases can migrate through the internal structure. Sublimation erosion removes material preferentially from certain regions, altering the nucleus shape and changing the patterns of solar illumination that drive future thermal evolution. As the thermal cycles continue through each 5.7-hour rotation of 3Y/Atlas, the nucleus undergoes gradual modification that will eventually alter its physical properties. Chemical composition and outgassing behavior. The intricate dance between heating and cooling, sublimation and condensation creates a dynamic system where ancient materials preserved for billions of years in the cold of space begin their transformation into the gas and dust that will eventually form the spectacular tail structures visible to observers on Earth. The thermal evolution represents one of the fundamental processes that govern cometary behavior and control how these primitive time capsules reveal their secrets as they encounter the warming influence of our star. As 3I/Atlas continues its inward journey through the solar system, the expanding envelope of ionized gas surrounding the nucleus begins to encounter Earth's extended magnetic environment. The magnetosphere that shields our planet from the direct impact of the solar wind. This interaction, subtle and largely invisible to ground-based observation, creates the first electromagnetic connection between the ancient comet and the world from which astronomers watch its approach. The comet's ion tail, still tenuous and barely formed, enters the outer regions of Earth's magnetic influence, where charged particles from the subliming nucleus experience forces and accelerations that reflect the complex geometry of planetary magnetic fields suspended in the flow of the solar wind. The magnetosphere of Earth extends far beyond the planet's atmosphere, creating a magnetic cavity in the solar wind that varies in size and shape depending on the dynamic pressure and magnetic field orientation of the streaming plasma. At its dayside boundary, the magnetopause, Earth's magnetic field meets the solar wind approximately 10 Earth radii from the planet's surface, while the nightside magnetotail extends downstream for hundreds of Earth radii in the anti-solar direction. Within this vast magnetic envelope, charged particles follow complex trajectories determined by the interplay between magnetic forces, electric fields, and gravitational influences that create one of the most intricate plasma physics environments in the solar system. The ion tail of 3I/Atlas, composed primarily of ionized water vapor, carbon monoxide, and other molecular species from the subliming nucleus, carries with it the electromagnetic signature of its formation in the solar wind environment. These ions, accelerated by the interaction between the comet's expanding coma and the streaming solar plasma, move at velocities of tens of kilometers per second in directions determined by the solar wind magnetic field configuration. As the tail encounters Earth's magnetic field, the comet ions experience additional forces that can deflect their trajectories and alter their energy distributions in measurable ways. Magnetic reconnection processes. The fundamental mechanisms by which magnetic field lines from different sources can merge and reconfigure become possible when the comet's magnetic environment encounters Earth's magnetosphere. The magnetic field carried by the solar wind and embedded within the comet's ion tail can connect with Earth's magnetic field lines under specific geometric conditions, creating temporary magnetic linkages that allow the direct transfer of particles and energy between the comet's plasma environment and Earth's magnetosphere. These reconnection events, though brief and localized, create electromagnetic signatures that can be detected by satellites monitoring the space environment around Earth. The Van Allen radiation belts, regions of trapped charged particles held within Earth's magnetic field, provide a sensitive detector for the passage of cometary material through the magnetosphere. Energetic particles from 3Y/Atlas that become captured within Earth's magnetic field add to the population of trapped radiation and create subtle changes in the energy spectra and spatial distribution of particles within the radiation belts. These changes, detectable by particle detectors aboard Earth-orbiting satellites, provide direct evidence for the injection of cometary material into the terrestrial space environment. Auroral phenomena. The luminous displays created when charged particles precipitate into Earth's upper atmosphere show subtle modifications during periods when cometary material interacts with the magnetosphere. The injection of particles with different energy and compositional characteristics than typical solar wind plasma creates variations in auroral intensity and spectral properties that can be distinguished from normal auroral activity. Molecular ions from the comet contribute emission lines not typically present in aurora, creating spectroscopic signatures that reveal the chemical composition of the comet's ion tail. The interaction creates electromagnetic waves that propagate through both the cometary plasma environment and Earth's magnetosphere, carrying information about the physical conditions at the interaction boundary. These waves, detectable as radio emissions in specific frequency ranges, provide remote sensing capabilities for studying plasma processes that occur far from direct observation. The wave characteristics depend on the density, temperature, and magnetic field properties of both the cometary and terrestrial plasma environments, creating a form of electromagnetic communication between these distant regions of space. Plasma instabilities develop at the interface between the comet's ion tail and Earth's magnetic field, creating turbulent regions where the two plasma populations mix and interact. These instabilities generate electric fields that can accelerate particles to high energies and create non-thermal distributions that differ from the equilibrium conditions expected for either plasma source. The turbulent mixing processes contribute to heating of both plasma populations and influence the transport of material and energy across the interaction boundary. The Earth's ionosphere, the electrically conducting layer of the upper atmosphere, responds to the electromagnetic disturbances created by the comet magnetosphere interaction through changes in electron density and current systems. Radio wave propagation through the ionosphere shows subtle modifications that correlate with the timing and intensity of cometary plasma encounters, providing ground-based detection capabilities for space-based interaction processes. These ionospheric signatures offer an additional diagnostic tool for studying the electromagnetic coupling between cometary and terrestrial environments. Magnetic field measurements from spacecraft in various regions of Earth's magnetosphere show perturbations that can be attributed to the passage of cometary magnetic field structures through the terrestrial environment. The strength and direction of these perturbations provide information about the magnetic field embedded within the comet's ion tail and the efficiency of magnetic field transport from the comet's interaction region to Earth's magnetosphere. The magnetic signatures evolve as the comet's activity level changes and the ion tail develops more complex structure. The gravitational influence of Earth on charged particles in the comet's ion tail creates additional complexity in the interaction dynamics. Ions with specific energy and pitch angle combinations can become temporarily captured in Earth's gravitational field while remaining influenced by magnetic forces, creating hybrid trajectories that combine aspects of both gravitational and electromagnetic motion. These gravitationally modified particle trajectories contribute to the spatial distribution of cometary material within the magnetosphere and influence the duration and intensity of interaction effects. Temporal variations in the interaction reflect both the changing activity level of 3y/8less as it approaches the Sun and the dynamic nature of Earth's magnetosphere as it responds to solar wind conditions. Periods of enhanced comet outgassing coincide with stronger electromagnetic signatures, while variations in solar wind pressure and magnetic field orientation modulate the efficiency of the interaction processes. The correlation between cometary activity and terrestrial space weather effects provides insight into the coupling mechanisms that govern plasma interactions in the solar system. The chemical composition of particles injected into Earth's magnetosphere from the comet's ion tail creates isotopic signatures that can be distinguished from solar wind material through mass spectrometry techniques. The deuterium enhancement and carbon isotope ratios, characteristic of cometary material, provide unique fingerprints that allow researchers to trace the transport and evolution of cometary particles within the terrestrial space environment. These compositional measurements offer direct chemical analysis of cometary material without requiring spacecraft missions to the comet itself. As the electromagnetic dance between 3I/Atlas and Earth's magnetosphere continues, the interaction creates a temporary but measurable connection between the ancient wanderer and our planet, linking the chemistry of the early solar system preserved within the comet's nucleus to the complex electromagnetic environment that surrounds Earth. The subtle forces and particle exchanges occurring in this interaction represent one of the many ways that cometary material continues to influence planetary environments billions of years after the initial formation of the solar system, carrying forward the chemical and electromagnetic heritage of our cosmic origins into the present moment. Across continents and beneath star-filled skies, amateur astronomers emerge from their homes carrying telescopes, cameras, and the patient enthusiasm that drives citizen science forward, one observation at a time. These dedicated observers, working with instruments ranging from modest backyard telescopes to sophisticated CCD imaging systems, begin to contribute their own measurements to the growing database of observations documenting 3I/Atlas's unusual color evolution. Their collective efforts, coordinated through online networks and astronomical societies, create a global monitoring system that operates continuously as Earth rotates, ensuring that the comet remains under observation throughout each 24-hour period, despite the limitations that constrain any single observatory site. The amateur astronomy community brings unique advantages to the study of rapidly changing phenomena like 3I/Atlas's color variations. Unlike professional observatories, which must balance many competing research priorities and often observe targets according to predetermined schedules, amateur observers can respond quickly to unusual developments and provide intensive monitoring of specific objects during critical periods. Their geographical distribution across time zones creates natural coordination that maintains continuous surveillance, while their flexibility allows for rapid adjustment of observing programs to focus on the most scientifically interesting aspects of the comet's behavior. Individual observers contribute measurements using equipment and techniques that span a wide range of sophistication levels. Visual observers, using nothing more than telescopes and their eyes, provide valuable estimates of brightness and color that can be calibrated against standardized comparison stars. Photographic observers capture images on film or digital sensors, creating permanent records that can be analyzed for precise measurements of brightness variations and changes in the comet's appearance over time. Advanced amateur astronomers employ photometric equipment and spectroscopic instruments that approach professional quality, contributing observations that meet the precision standards required for scientific analysis. The coordinated observing campaigns organized by amateur astronomy groups create datasets with temporal resolution that exceeds what any single professional observatory could achieve alone. By organizing observers to make measurements at specific times throughout the night and across different geographical locations, these campaigns capture variations in the comet's properties that might otherwise be missed by observations separated by days or weeks. The high temporal resolution proves particularly valuable for studying the rapid color changes that characterize 3Y/Atlas's unusual behavior. Online databases and communication platforms allow amateur observers to share their measurements in real time, creating immediate feedback that helps identify instrumental problems, atmospheric effects, or other systematic errors that might compromise data quality. The collaborative verification process, where multiple observers confirm each other's results, provides quality control that ensures only reliable measurements contribute to the scientific analysis. The transparency of data sharing also allows researchers to understand the methods and limitations associated with each observation. Critical information for properly interpreting the assembled dataset. The diversity of instruments and techniques employed by amateur observers provides multiple independent checks on the reality of observed phenomena. Color measurements made visually through telescopes can be compared with photographic color indices derived from digital images, while brightness estimates from different observers using different equipment provide redundancy that helps identify and eliminate systematic errors. This multi-method approach proves particularly valuable for confirming subtle effects like the overnight color changes that first brought 3I/Atlas to scientific attention. Educational institutions contribute to the amateur observing effort through student projects and classroom activities that combine learning objectives with data collection. High school and college students, guided by instructors with astronomical training, operate modest telescopes and imaging equipment to document the comet's evolution while simultaneously learning about cometary physics, photometry, and data analysis techniques. These educational observations, while perhaps less precise than those made by experienced amateur astronomers, add to the overall database and help train the next generation of observers. The enthusiasm that drives amateur participation in cometary observation reflects the fundamental human fascination with rare and unusual celestial phenomena. The knowledge that they are witnessing something that occurs perhaps once in a lifetime motivates observers to endure cold nights, equipment failures, and cloudy weather in pursuit of measurements that contribute to scientific understanding. This intrinsic motivation often leads amateur observers to achieve levels of dedication and persistence that exceed what might be expected from casual interest in astronomy. Technological developments in amateur astronomy equipment continue to expand the scientific contributions possible from modest budgets and backyard observing sites. Modern CCD cameras provide sensitivity and precision that surpass photographic methods, while computer-controlled telescopes allow for automated data collection that can continue throughout the night without constant human supervision. Affordable spectrographs make it possible for advanced amateurs to contribute wavelength-resolved measurements that complement the photometric observations made by their colleagues with simpler equipment. The global nature of amateur astronomy networks creates opportunities for around-the-clock monitoring that takes advantage of Earth's rotation to maintain continuous surveillance of rapidly changing targets. As 3 I/Atlas sets below the horizon for observers in North America. Their counterparts in Europe and Asia begin their observations, creating seamless temporal coverage that captures variations occurring on timescales shorter than the length of night at any single location. This global coordination proves essential for understanding phenomena that evolve rapidly compared to the daily cycle of terrestrial observation opportunities. Quality control procedures developed by amateur astronomy organizations ensure that contributed observations meet standards appropriate for scientific analysis. Standardized measurement techniques, calibration procedures, and reporting formats help minimize systematic differences between observers and instruments. Regular comparison campaigns, where multiple observers measure the same standard stars or well-characterized variable objects, provide opportunities to identify and correct systematic errors that might otherwise compromise the scientific value of contributed measurements. The archival value of amateur observations extends far beyond their immediate scientific applications, as the accumulated database of measurements provides historical records that become increasingly valuable over time. Future researchers studying cometary behavior, orbital evolution, or the statistical properties of the comet population will benefit from having detailed observational records of objects like 3 I/Atlas that exhibited unusual or extreme behavior. The preservation of these observations in digital archives ensures their availability for future analysis using techniques and theoretical understanding that may not yet exist. Social media platforms and online forums create communities where amateur observers share their experiences, coordinate observations, and discuss the scientific implications of their measurements. These virtual gathering places foster collaboration between observers separated by vast distances and provide forums for asking questions, sharing techniques, and celebrating successful observations. The social aspects of amateur astronomy contribute to sustained participation and help maintain the enthusiasm necessary for long-term monitoring projects. The integration of amateur observations with professional research programs creates partnerships that benefit both communities. Professional astronomers gain access to observational coverage and temporal resolution that would be impossible to achieve with limited telescope time and resources, while amateur observers receive feedback about the scientific significance of their contributions and opportunities to participate in cutting-edge research. These collaborations demonstrate the continuing importance of citizen science in an era of increasingly sophisticated and expensive professional instruments, as amateur astronomers around the world continue their patient vigil, documenting each subtle change in 3 I/Atlas's appearance through the long hours of darkness. Their collective efforts create a comprehensive record of one of the most unusual cometary displays in recent memory. Their dedication ensures that future generations of scientists will have access to detailed observational data that captures every nuance of the comet's evolution, preserving for posterity the measurements that document this brief but remarkable visitor's passage through our cosmic neighborhood. The elliptical path that carries 3 I/Atlas through the solar system encodes within its mathematical precision a gravitational autobiography spanning billions of years of cosmic encounters. Each slight deviation from a perfect Keplerian orbit preserves the memory of close approaches to massive bodies, the accumulated influence of planetary perturbations, and the subtle effects of non-gravitational forces that have shaped the comet's trajectory since its formation in the outer reaches of the primordial solar nebula. This orbital evolution, written in the language of celestial mechanics, tells the story of how a small world born in the cold depths beyond Neptune has wandered through gravitational resonances and chaotic regions to arrive at its current rendezvous with the inner solar system. The semi-major axis of the comet's orbit, measuring approximately 180 astronomical units, places its aphelion in the remote region where the Sun's gravitational influence weakens to the point where passing stars can exert measurable perturbations on cometary trajectories. At this extreme distance, 3I/Atlas spends the majority of its orbital period in the deep cold, where temperatures approach the cosmic background radiation level and sublimation processes remain completely dormant. The comet's velocity at aphelion measures mere tens of meters per second, so slow that a person could outrun the ancient wanderer as it crawls through the outermost reaches of the solar system. Gravitational perturbations by the giant planets have repeatedly modified the comet's orbital elements over the course of its long journey around the Sun. Each passage through the outer planetary region subjects 3I/Atlas to gravitational forces from Jupiter, Saturn, Uranus, and Neptune that can alter its semi-major axis, eccentricity, and inclination through complex three-body interactions. The most significant perturbations occurred during close approaches to Jupiter, whose massive gravitational field can change a comet's orbital energy by amounts equivalent to thousands of years of gradual evolutionary processes. Numerical integration of the comet's orbital evolution backward in time reveals a history of chaotic motion characteristic of objects in the scattered disk population. Computer simulations following the gravitational influences of all major solar system bodies show that 3I/Atlas has experienced dozens of significant planetary encounters over the past million years, each one slightly altering its trajectory and contributing to the orbital evolution that brought it to its current perihelion distance of 0.3 astronomical units. The chaotic nature of this evolution means that small changes in initial conditions lead to dramatically different orbital histories, making it impossible to determine with certainty the comet's exact path more than a few million years into the past. The high orbital inclination of 3I/Atlas, tilted nearly 85 degrees relative to the plane of the solar system, suggests formation in a region of the early solar nebula where the gravitational influence of the giant planets was insufficient to enforce coplanar motion. This inclination, combined with the comet's retrograde orbital motion, indicates origin in the outermost regions of the forming solar system where materials are accreted under conditions of low gravitational binding and high orbital eccentricity. The preservation of this inclined orbit through billions of years of evolution demonstrates the stability of certain orbital configurations even in the presence of planetary perturbations. Tisserand invariant calculations provide insight into the dynamical relationship between 3I/Atlas and the giant planets, particularly Jupiter, whose gravitational dominance shapes the orbital evolution of most comets in the outer solar system. The Tisserand parameter, a quantity that remains approximately constant during gravitational encounters, indicates that 3I/Atlas belongs to the long-period comet population with orbital characteristics that distinguish it from the more frequently observed Jupiter family comets. This classification has implications for understanding the comet's formation location and the processes that delivered it to the inner solar system. Non-gravitational forces, primarily radiation pressure and outgassing-induced rocket effects, contribute additional complexity to the comet's orbital evolution as it approaches the Sun and begins active sublimation. The asymmetric emission of gas and dust from the rotating nucleus creates jet-like forces that can accelerate or decelerate the comet depending on the orientation of active regions relative to the direction of motion. These non-gravitational accelerations, though small compared to gravitational forces, accumulate over multiple orbital passages and can significantly alter the comet's trajectory over long time periods. The orbital period of 3I/Atlas, currently estimated at approximately 1,400 years, places it in the intermediate category between short-period comets that return frequently and the truly long-period comets with orbital periods measured in tens of thousands of years. This intermediate period suggests a complex evolutionary history involving multiple gravitational encounters that gradually reduced the comet's orbital energy from its original values in the Oort cloud. The current period represents a temporary phase in an ongoing orbital evolution that will continue to modify the comet's trajectory through future planetary encounters. Secular resonances, regions where the precession frequencies of orbital elements match those of the planets, can trap comets in specific orbital configurations for extended periods or provide escape mechanisms that allow sudden changes in orbital characteristics. The orbital elements of 3Y/Atlas place it near several secular resonance boundaries where small perturbations can lead to large-scale orbital evolution. These resonances create windows of enhanced dynamical sensitivity where the comet's orbit becomes particularly susceptible to modification by planetary perturbations. Close approach distances to the terrestrial planets during the comet's current orbital passage provide rare opportunities for detailed study of its physical and chemical properties. The minimum distance to Earth, achieved approximately 6 months after perihelion, brings 3I/Atlas within 0.2 astronomical units of our planet and creates observing conditions that will not be repeated for more than a millennium. This close approach, combined with favorable observing geometry, makes the current apparition particularly valuable for advancing scientific understanding of long-period comet characteristics. The orbital evolution of 3Y/Atlas demonstrates the interconnected nature of gravitational dynamics in the solar system, where the motion of small bodies preserves information about the distribution of mass and the history of planetary migration over billions of years. Computer simulations of early solar system evolution suggest that the current orbital characteristics of long-period comets reflect the gravitational fingerprints of planetary migration events that occurred during the first few 100 million years after solar system formation. These comets serve as gravitational fossils that preserve dynamical information about processes that shape the architecture of planetary orbits. Astrometric measurements of the comet's position against the stellar background provide the observational foundation for determining orbital elements and predicting future positions. The precision of these measurements, limited by atmospheric turbulence and instrumental capabilities, directly influences the accuracy of orbital determination and the reliability of long-term trajectory predictions. Improvements in astrometric precision through space-based observations and advanced ground-based techniques continue to refine understanding of cometary orbital evolution and enhance capabilities for predicting future apparitions. The gravitational memory encoded within the orbital characteristics of 3I/Atlas connects the present observation of this ancient wanderer to the vast scales of cosmic evolution that govern the motion of small bodies throughout the solar system. Each measurement of position and velocity adds to the accumulated knowledge of how gravitational forces have sculpted cometary trajectories over geological time, preserving within mathematical parameters the record of encounters and interactions that span the history of planetary formation and evolution. The orbit remembers what direct observation cannot access, carrying forward through space and time the gravitational heritage of our solar system's dynamic past. As 3I/Atlas reaches the closest point in its long elliptical journey around the Sun and begins the gradual retreat toward the outer darkness from which it came, the chemical fingerprints captured during its brief period of peak activity begin to fade like footprints in cosmic sand. The intense outgassing that created the spectacular emissions now diminishes as solar heating weakens with increasing distance, but the spectroscopic data collected during the comet's active phase preserves a detailed chemical record that will continue to yield scientific insights long after the comet itself returns to dormancy in the cold reaches beyond the orbit of Neptune. The molecular emission lines that dominated the comet's spectrum during its closest approach to the Sun gradually weaken as decreasing solar flux reduces the rate of photoexcitation processes that create the characteristic fluorescence of cometary gases. Water vapor production, which peaked at several tons per second during perihelion passage, drops exponentially as surface temperatures fall below the threshold necessary to sustain vigorous sublimation. The blue-green emissions from carbon molecules that first caught astronomers' attention months earlier fade to barely detectable levels as the production of parent molecules decreases and photodissociation processes become less efficient in the weakening solar radiation field. The isotopic signatures preserved within the spectroscopic measurements provide permanent chemical records that encode information about conditions in the early solar system and the processes that governed cometary formation. The enhanced deuterium to hydrogen ratios detected in water molecules preserve evidence for formation temperatures below 30 Kelvin, conditions that existed only in the outermost regions of the solar nebula where 3 Ice/Atlas accreted from primordial ice and dust. These isotopic fingerprints remain accessible to analysis long after the comet's active phase ends, providing scientists with samples of early solar system chemistry frozen in time and preserved in digital archives. Carbon isotope measurements reveal the complex mixing processes that incorporated materials from multiple sources into the growing nucleus during its formation billions of years ago. The variations in carbon-13 to carbon-12 ratios between different molecular species reflect the temperature and chemical conditions under which various carbon-bearing compounds formed in the early solar nebula. Some molecules show isotopic signatures consistent with formation through ion molecule chemistry in cold molecular clouds, while others exhibit ratios that suggest high-temperature processing in the inner regions of the forming solar system before being transported outward and incorporated into the comet's structure. Nitrogen isotope anomalies detected in hydrogen cyanide and other nitrogen-bearing compounds provide some of the most extreme values ever measured in solar system materials, with nitrogen-15 enhancements that approach levels observed in certain pre-solar grains believed to have formed in the envelopes of dying stars. These isotopic signatures suggest that 3 Ice/Atlas incorporated materials that experience nuclear processing in stellar environments before being expelled into interstellar space and eventually incorporated into the solar nebula. The preservation of these signatures within the comet's chemical structure makes it a valuable repository of information about galactic chemical evolution. Oxygen isotope measurements contribute additional constraints on the thermal and chemical environment during the comet's formation, revealing evidence for photochemical processing that occurred in the